Okay, Math 12s. So I thought I'd go back through our notes from section 3.3 on the factor theorem and just make a quick video of that to help you out. So we started, if you'll recall, we started with a review of the remainder theorem. And we took this polynomial function and divided by x minus 3. Now you'll notice that there was no cubic here and there was no second degree variable. So we put that in. I put negative 4x to the 4 plus 0x cubed plus 0x squared to hold place values plus 11x minus 7. And with synthetic division, we used our coefficients, negative 4, 0, 0, 11, and negative 7. And then we used the a value here of 3 to do our synthetic division. So we brought the negative 4 down, and then went 3 times negative 4 to get negative 12. 0 plus negative 12 to get negative 12. 3 times negative 12 to get negative 36. Added those to get negative 36. 3 times that to get negative 108. Added those to get negative 97. 3 times negative 97 to get negative 291, and then added those to get negative 298. And that was my remainder. So over here you'll see the quotient. The quotient has these coefficients and 1 power less, 1 degree less than the original polynomial. So negative 4x cubed minus 12x squared minus 36x minus 97 with the remainder of negative 298. Now we can take a look at long division, just to do a quick review of that as well. And of course you can pause and go back over how those numbers happen in the synthetic division. Play it again if it's a little too fast for you. Then let's take a look at long division. We've also done that before. So the question we can do, or we can ask ourselves when we do long division, is what do we multiply x by to get 6x squared? That answer, of course, is 6x, so we write that answer up here. 6x times x is 6x squared, and 6x times 1 is positive 6x. Of course, we subtract those. 6x squared minus 6x squared is 0. And negative 1x minus 6x is going to be negative 7x. What do we multiply x by to get negative 7x? Negative 7. Negative 7, oh, and sorry, don't forget to carry down the 1. Negative 7 times x is negative 7x, and negative 7 times 1 is negative 7. We subtract those again, those cancel. And 1 minus negative 7 is like saying 8. So we get a remainder of 8. Now, if I was to do a division statement in this form, this would be my polynomial. So 6x squared minus 1x plus 1 divided by my divisor, x plus 1, is equal to my quotient, 6x minus 7, plus my remainder over my divisor, x plus 1 again. And there you have your division statement and long division. So we moved on to talk about the remainder theorem. The remainder theorem allows us to determine the remainder of some polynomial divided by x minus a by calculating p of a, meaning substituting the a value in to the polynomial. So for 6x squared minus x plus 15 divided by x plus 1, my a value is negative 1. Remember, x plus 1 is like saying x minus negative 1. That's my a value. So this becomes 6, negative 1 squared minus negative 1 plus 15. Negative 1 squared is 1, and 6 times 1 is 6. 6 minus negative 1 is like saying 6 plus 1, and plus 15. So 7 plus 15 gives us 22, a remainder of 22, which, if I look back here, I know what happened. All right, let's take a little tweak here. If you look back at your notes, you'll notice this wasn't 6x squared minus 1x plus 1. It was plus 15, which meant I carried down a 15 here. And 15 minus negative 7 was 22. Seemed that was a little different than what I remembered. There we go. Hopefully you can catch that in your notes. All right, so we've got our remainder theorem. It allows us to calculate the remainder if we plug in the a value and substitute it into the place of x in our polynomial. Who cares? Well, we do, if the remainder is 0. The factor theorem says that if I have some polynomial, for any polynomial p of x, x minus a is a factor if the remainder, according to the remainder theorem, is 0. So if the remainder of polynomial divided by x minus a is 0, then x minus a is a factor. Okay, so we talked about that, and that becomes very useful to us. So here's an example. X squared plus 5x plus 4 divided by x plus 1. So determine if x plus 1 is a factor of p of x. We test that by plugging in the a value. And like you see over here, we're always thinking in terms of x minus a. So for x plus 1, that's like saying x minus negative 1. So we're going to substitute negative 1 in for x to get negative 1 squared plus 5 times negative 1 and plus 4. Negative 1 squared is 1 minus 5 plus 4, and that equals 0. So if the remainder is 0, then x plus 1 is a factor of x squared plus 5x plus 4. Okay, it's a factor because we got a remainder of 0. I then went on to say that if x minus a is a factor, then p of a will be 0, and the converse is true as well. If p of a is 0, then x minus a must be a factor. So we went on to a second example. And in the second example, it's a common question, which binomials are factors of? So they gave us 4 binomials here. We have x minus 1, x minus 2, x plus 2, and x plus 3. And we're going to test them by taking the a value. So in this first case, the a value is 1, whatever comes after the negative sign. So p of 1 is 1 cubed plus 4 times 1 squared plus 1 minus 6. So that's 1 plus 4 plus 1, that's 6, minus 6 is 0. Therefore, x minus 1 is a factor. In the second case, we plugged in the 2, right? X minus 2, so our a value was 2. 2 cubed plus 4 times 2 squared plus 2 minus 6. Well, 2 cubed is 8, 2 squared is 4, and 4 times 4 is 16, plus 2 and minus 6. 8 plus 16 is 24, plus 2 is 26, minus 6 is definitely not 0. Therefore, x minus 2 is not a factor. In the third example, we were looking at x plus 2. Now recall that x plus 2 is like saying x minus negative 2. So that's the a value. That's the value that I'm substituting in. So p of negative 2 is negative 2 cubed, which is negative 8. 4 times negative 2 squared, which is still 16. Right? Negative 2 times negative 2 is 4. Times 4 is 16. Plus negative 2 is like saying minus 2, minus 6. Well, negative 8 plus 16 is 8. Minus 2 is 6, minus 6 is 0. So that is a factor. And the last one, negative 3 cubed is negative 27. Negative 3 squared is 9, times 4 is plus 36. Plus negative 3 is minus 3 and minus 6. So negative 27 minus 3 is negative 30. Minus 6 is negative 36. Plus 36 is 0. Therefore, x plus 3 is a factor. So we've got 3 factors, x minus 1, x plus 2, x plus 3. And in a cubic, that's the maximum number of factors I can have. So I think I've got them all. So x minus 1 times x plus 2 times x plus 3 are the factors of, and are equal to, x cubed plus 4x squared plus x minus 6. Now, I want you to notice something here. Let me get my little highlighter out. That negative 1 times positive 2 is negative 2, times positive 3 is negative 6. So if my factors have the form x minus, well, just x plus or minus a, then the constants must be equal to the constant of the polynomial, the product of the constants. Okay, so note that the product of the constants in the factors is equal to the constant in the polynomial. Again, you can pause that and take a look at it, take it in. I'm going to keep on going here. So that means that if you know all but one of the factors, you can determine the last factor by observation. At least that's true if your polynomial has a coefficient, a leading coefficient of 1. Okay, it doesn't work if this is a 2 or a 3. Okay, but if it's a leading coefficient of 1, you can figure this out. So if we knew the first two, negative 1 and 2, negative 1 times 2 is negative 2, negative 2 times something equals negative 6, and of course that something must be positive 3. So I would have been able to build my third factor. All right, in example 3, you were asked to factor fully this cubic function with a leading coefficient of 2. So in order to factor, we look for, we test numbers that are factors of the constant. So for P of x, we evaluate P of a for factors of the constant. That's what it means. So we're going to test only numbers that could possibly multiply together to make -2. And that's positive or -1 and positive or -2. There's no point in testing 3 and 4 and 5 because I can't multiply 3, 4, and 5 by an integer to get -2. So I test P of 1, 2 times 1 cubed plus 3 times 1 squared minus 3 times 1 minus 2, and lo and behold, it equals 0. That means x minus 1 is a factor. We went through and tested some other numbers and found out that x plus 2 is a factor as well, but then we were kind of stuck because we had these two factors, but the third one had to be 2x minus something in order to get a 2x cubed. So we've only found two factors, and then we're stuck, so arg. How do we find the third one? Well, there's a fast way. So what I said was, instead, find one factor and then use division to find the rest. So using that factor that we found, x minus 1, I did synthetic division. So I just double check, make sure that all my exponents are there, 3, 2, 1, and 0, x to the 0. I plugged in my coefficients and my constant term. I took the a value, which was 1, carried down the 2, 1 times 2, 3 plus 2 is 5, 1 times 5, -3 plus 5 is 2, 1 times 2, -2 plus 2 is 0. And these 2 and 5 and 2 made up my next polynomial, a quadratic polynomial. 2x squared plus 5x plus 2 is another factor because my remainder is 0 when I do the division. And this, being a quadratic, can be factored. So I looked for two numbers that multiply to give 4 and add to give 5. Those numbers were 1 and 4. Using decomposition, I broke that middle term up into 1x and 4x. So 2x squared plus 1x plus 4x plus 2. I looked for a common factor in the first two, which was x. That left me with 2x plus 1, which I immediately wrote again, and then asked myself, what do I multiply 2x by to get 4x? And that had to be positive 2. Double checking, 2 times 1, does that equal 2? Yes. So my common factor was 2x plus 1, I wrote that first, and my leftover bits were x and plus 2, so I wrote that second. That means that my factors were x minus 1, the first one I found, x plus 2, and 2x plus 1, the other two that I just discovered. The last thing we looked at was how we could use a formula, and to determine the formula for the volume of some rectangular block to determine the possible dimensions of that block. So we drew out a little rectangular prism here and talked about, the length as being factor 1, the width as being factor 2, and the height as being factor 3. Well, in order to figure out those factors, we need to go through the process that we just did. We start by looking at the factors of the constant term, -8. So we're looking at positive and -1 and 2 and 4 and 8. Those are the numbers that in some way, shape, or form I could multiply a couple of them to get -8. When I plugged 1 in, 6 times 1 plus 25 times 1 plus 2 times 1 minus 8. Well, there's no way that was going to work, so I didn't even bother. -1, possibly. So 6 times -1 cubed was -6. 25 times -1 squared was 25. 2 times -1 was -2, but that didn't work either. We tested 2, which wasn't going to work. In fact, any of the positive numbers wasn't going to work. Tested -2. I'll let you test that on your own. 4 didn't work. We knew it wasn't going to. But -4 finally did. Took a little while to get there, but we got to -384 plus 400 minus 8 minus 8, and that equaled 0. That meant that x plus 4 was a factor. There we go. So x plus 4 is a factor. So, with the coefficients and the constant term of that original cubic function, we did synthetic division using -4. So brought down the 6. -4 times 6 was -24, etc. We got a remainder of 0, which is good. We used the 6, the 1, and the -2 to make a quadratic. Right? 6x squared plus 1x minus 2. Factored that, and then it ended up with x plus 4. Ended up with 3x plus 2 and 2x minus 1. 3x plus 2, common, and the leftover bits, 2x minus 1. So my three factors are the original and my new 2, and those make up my dimensions. So my length, my width, and my height. There you have it. I gave a brief assignment out of our textbook. I also encourage you to look at example 3, page 130, for how to work with a quartic. Same stuff as what we did with the cubics, just longer. All right, bye-bye.